Good afternoon, everyone. My name is Csaba Fitzl, and welcome everyone to our exploit generation and JavaScript analysis automation with WinDebug. A few words about ourselves. I have way too much information about myself on Google or on the internet, so if you want to know anything about me, just Google up my name, and you will probably know my entire life. Back to school. I have a wife and a 3-year-old son, and I love hiking as my #1 hobby, and of course the second one is security. And I have plenty of certification. For some reason, I just love to do them. I have plenty of unimportant ones and a few more useful ones, like the ones from offensive security. Miklos?
Hey, hello folks. So my name is Miklos Desbordes, and as opposed to what Csaba was saying, I'm the dark person, so I don't have too much information published about myself on the net, so I challenge you to find anything about me. Probably you'll find something from this week, but not too much before that. So that said, I'm also married. I have 2 beautiful kids, and I'm also a hobbyist hacker. But aside from spending hours before the screen, I also do a lot of hiking, and each year I try to do a bit of a challenge to try a new sport. So I have a lot less certificates than Csaba has, because he's an absolute champion at that. But the one that's probably relevant for today is a JAX RAM, so JAX reverse engineering malware. So with that, back to Csaba.
Thank you. So the first part is the automated exploit generation. So it all started, the entire idea of it. Making exploits, it kind of can be, or actually it is a really heavily manual process when you start it. Because basically when you load the application, crash it for the first time, you need to go around, discover the memory layout, check the registers, which of them points to where, and so on, calculate offsets, calculate your space on the buffer, and so on and so on. Not speaking about when you load the application debugger and you start to develop your exploit, and maybe you forget to set your breakpoint and the application just crashes. Oh, I forgot it. Okay, let's start it over. You start the debugger, you attach the process, you crash it again, you forgot to set the breakpoint again, then you maybe make a mistake with your shellcode or with a memory address. By mistake, you make the memory address in big endian instead of little endian, and you always have to start the process, start the debugger, attach it, and so on. And this is quite time-consuming to be true. And if you actually look how you develop an exploit, and we are talking here about basic buffer overflows, it's pretty standard. And basically what you do, once you have the crash, so we are not talking about the fuzzing part here, it's just when you already know that you can control EIP and then develop the exploit, you need to find the EIP overwrite location, so find the offset on your buffer, and then you will examine the memory layout for all the offsets, for the space, the registers, what can you play with it, and so on. Then you need to find a way to jump to your shellcode, typically like jump ESP and so on, but you can use jump other registers or call any of the registers, or just push the register value and then return to it. And then you need to find an address in the memory which actually contains this small assembly instruction that you can use on your exploit. And then you need to generate the shellcode in Metasploit typically, and then put it all together, and if all goes well, you manage to develop an exploit. But again, this can be a lot of time, even for simple buffer overflows. So I thought that my task, or I came up with this idea that why not automate the entire process? There are tools like Mona that already does a great job for you for many of the parts. but doesn't automate the entire flow. And again, this is for most of the cases. Of course, there are corner cases, and there will be always corner cases. For typical buffer overflow, it's just, again, a standard process. So the idea was to develop some tool which can create a working exploit from a crash, like a proof of concept, if possible with zero manual interaction. So I wrote a module in Python which uses the py-kd library to interact with WinDebug. This limits this entire tool currently to Windows applications. py-kd is a very powerful Python library that can interact with WinDebug. It's developed by a Russian team. They don't really have a name of the group. It's a few developers. You can just Google it, and you will find all the people participating in that project. And basically, it allows you to even start WinDebug from Python, attach the process, or just start the entire process in Python without really opening WinDebug. And it can send and use all of the WinDebug commands from Python, and you can get those output and you can use them. Or it has a very rich API, which allows you to read register values, read pointers, search the memory, and so on. So again, this is really powerful, and actually the tool is already released on GitHub, and we will put the link at the end of the presentation. So what can it do? Again, at this point, it only works for basic buffer overflows. It can bypass ASLR if the application has a module or DLL which doesn't have the ASLR bit set. So it uses one of the methods to bypass it. And you can set it on the command line if you want to look for that or not. It works for network and file-based exploits. It's important because the workflow, it's a bit different. So if your exploit is file-based, like an MP3 list, then you need to actually generate the file and then open the application and open the file, while with network-based exploits, you actually need to start the application and then send the exploit after. And it will create a successful exploit from the simple crash, and it automates the entire process. Unless you need to interact with the application for some reason, but if not, then basically you don't have to touch it. And you don't need to start WinDebug or anything, because the script will start the process inside WinDebug already. So what's the logic of the application? How does it work? It will find the EIP overwrite location, the offset for that. It uses the pretty much same method that most people usually do. It will create a pattern and then find the offset for that pattern. Then it will find registers pointing to your buffer. Then it will find all the bad characters that is not cool from the exploit point of view. It will basically go over all the 256 options. And then it will find a way to jump to your shellcode using maybe a jump instruction or a call instruction or something else. It will generate the shellcode. Now for this one, it will use Metasploit to generate the shellcode. I didn't want it to reinvent the wheel here. At this point, the script is hard-coded to generate a shellcode to start calc.exe, but it's basically you just replace one line in the script, what kind of shellcode you want to generate. Basically, you have to enter the Metasploit command itself. And it will read back the shellcode, put it all together, and run the exploit. And it will also save the exploit if you want. In case it's a file-based, then it's already saved. If it's a network-based, you need to do some writing, but it will essentially create a Python script for you, which will save the, or which will run the exploit. So I have a demo here, and hopefully all goes well. So let me delete this file. Okay, so the first example is Minishare. I think if you started with exploit development, you probably came across SecurityTube, and they are using Minishare there as well as an example. It's pretty old, but I think it's great for education. So basically, I just start the script here, and I will let it run and then go back for the logs. It will log all the important parts of the exploit development. As you can see, it's always starting Minishare and restarting it for all the various steps. At this point, it's looking for bad characters. Well, I will scroll back in a minute. Now it's generating shellcode. It takes a few seconds, and at the end, we will see a calc popping up. Oh, that's great. This is the first time I got calc popping up at the front and not somewhere in the background. So let's see what happened here. So is it seen good enough, or you want me to zoom in even more, maybe a bit more? So it will send in a pattern for Minishare, then it will identify what is the pattern that overwrote AIP. It will identify the offset. There are some exceptions around because maybe some of the registers are uninitialized or pointing to an uninitialized memory space. And they will throw an exception, but it just ignores that. Then it will calculate the space you have on the buffer, and then it will start looking for the bad characters, identifying all of them. It will take a list of them, and this will be used when generating the shellcode with Metasploit. Now, it already knows which registers is pointing to your buffer, so it will try and, in case this is ESP, and it will try to find jump ESP in the loaded modules, so it will go through all the loaded modules and search through them, and it will log how many assembly instructions it found in that module that you can use. At the end, it will list all of them, all the memory addresses. It will pick up the first one, or actually it will pick up any of those that doesn't contain a bad character. So this list will be filtered. It will generate the shellcode, but this is Metasploit at the end, and it will run the exploit. And then we have the calc in this case. But what it also did, it created a Python script, which is basically the actual exploit, and not much is seen here. Yeah, the message is there, but this Python editor doesn't display it very well. Anyhow, if I start Minishare, and I have this Minishare exploit Python script, which was generated by this. I start it, and then you have a calc in the background. So it works. And I can show another demo with another one, the EasyRM. That's a MP3 player. Basically, it will do the same here. This is a file-based exploit, so it has to create an M3U file in order to crash the application. Now, luckily, the application has a command line option to load the M3U file, so I don't need to interact with it. But if it didn't have, I probably need to go every time to the application, load the file, and crash it. And once the crash happened, the script will take over again. So basically, you only need to load the application, then we have calc again. And if I open the application and load the file, this list M3U is generated. Okay, I will skip that, but basically that file was used to actually create the exploit. I'm not sure why it didn't do it properly manually. Anyhow, let me switch back to the presentation. So I have video here just in case it didn't work, but it worked, so no need to show that. How to use it? Now, there is some pre-work that has to happen because we need to dynamically build the exploit. So I actually need to dynamically build the buffer sent to the application. And for that, I need to interact with it. And I just choose making the exploit as a class. And basically, you have to populate that class with some initial info. And basically, that's mainly the exploit function. But let me go to my text editor and show it here. Let me choose this one. So basically, in the exploit function, you define the actual crash, the POC, and then you have this buffer variable, which will be a list of strings, and you need to do a join on the strings what will be sent into. But other than that, if you have a POC Python code, you basically copy it to this part. There are some other things that you need to specify if it's a file-based or not. You need to specify the command for the actual application. If it's a file-based exploit, it's best to define the file name as well, because you will need to save a file. And there is a save option as well, which basically writing out the function you have here to a file, and that's all. That's it. And if it's a file-based, then the saving is just a pass because the file should be already saved and there. So as for the future of this application, so I think this can be easily developed further for SEH-based exploits, to add some more logic around more tricky jumps to your shellcode, or if your buffer is more tricky, it's also possible to develop a DP bypass with developing rope chains dynamically. But at this point, it doesn't know them. It's just for basic buffer overflow. Thank you.
All right, let me see if I can transfer the screen.
Yeah.
Okay. Okay, so funny thing is that both Csaba and I attended the very same magnificent exploitation training provided by Corlan. But we took very opposite angles of looking at what's possible with the very same set of tools. So can we use the very same technology for blue teaming, or kind of doing reverse engineering? Typically, when it comes to browser exploits, reversing them is time-consuming. You have a bunch of challenges. Any reverse engineers out in the room? Okay, a few hands. So you wouldn't want to waste your time on code that is not actually malicious, right? So first, the whole thing comes up with an automated sandbox flagging on suspicious behavior, or the level 2 team notices something funny, and then the thing lands on your desk. So what the next steps are, you typically end up looking at an obfuscated source code, typically a JavaScript code with a heavy obfuscation that eventually exploits some browser vulnerability. Let's just assume it's a use after free situation. And then uses a bit of a shell code to put it into a heap location and then run it. So there are a number of challenges associated with this. Like if you're analyzing this inside the native debugger, the browser's built-in debugger, I mean, you first have to spend a bit of time of figuring out where to put the breakpoints, if it's possible to put the breakpoints in the locations that you need to at all. Then you can actually rip the code out of the HTML page and have it analyzed in the external JavaScript engine. But then again, you are not having any references any longer to the DOM objects. So if in any chance the JavaScript still refers back to certain DOM objects, it will no longer work. Also, a bunch of JavaScript code that we've seen in the wild implements some sort of anti-debugging or anti-reversing techniques. So trying to detect whether it's being debugged and either not working or working differently. So the methodology really is to deobfuscate, catch the function before they execute, set up the breakpoint or even the overloading of the functions if that's your way to do it, and then locate the exploit code and understand the shell code that happens to be behind it. Now, a word of warning, we're not going to release something that will address all your problems that it would ever come up with reverse engineering browser exploits, but we're trying to let loose something of an idea on how you may want to do it differently than most people are doing. So JavaScript obfuscators use several techniques to achieve their goal. They use variable name mangling, they do character substitutes, function expressions like arrow functions, lambdas, ifs. Most often, they literally go back to evals. Word of note is that, gladly, since JavaScript is not really a class-based language, we don't have to deal with reflections because that would add enormous complexity to it. Now, the first part is deobfuscating. Now, there's a bunch of deobfuscators out there, like dozens literally, that pretty much do their work, and we don't really want to kind of reinvent the wheel, but we want to look at a kind of a different case that does reinventing the wheel in a very different manner. We want to make it sure that the JavaScript code is impossible. So make it impossible for the JavaScript code to realize it is being debugged. We want to have the malware run its in normal, native, natural environment, the browser itself. And if possible, stop at the exploit with the least amount of interaction. So we've seen a number of cases when people were trying to tell us that use whatever tools available to rip out the code from the HTML page and drop it into an external engine. That very often fails. So breaking out of the jail has failed way too many times for me. So I thought, why not try to break into it? Now, a lot of people shy away from WinDebug because it doesn't have a very nice user interface like much of the immunity debugger or all the debug has. But it comes at the advantage of WinDebug that it's awesomely easy to script it, especially if you're using the Python extensions for it, so PyKD. We are releasing the code after the conference, but my point is not really so much in releasing the tool, but rather releasing the methodology. So we're releasing a tutorial on how to go about this and how to figure it out on yourself. Worthy of note that browser implementations differ significantly. IE8 versus IE10 versus IE11 versus Edge versus Chrome, they all have very different implementations of the JavaScript engine, literally each of them. So for our tools to work, you actually have to figure out for each of them how you can do the debugging. So the current tool that we are releasing is set for IE11 and IE8. It's deobfuscating the eval-based code and is logging each session to a separate file. And as much as possible, it's automating the entire process. So not sure how many of you have tried to debug browsers from WinDebug. One of the challenges is to attach the browser to the debugger. Attach the debugger to the browser, sorry. Typically, browser processes have a lot of separate threads, separate processes, and you have to figure out which one to attach to. If you want to open the WinDebug session and try to run the browser out of it, it will just not work the way you intend it to. So first you have to spawn the browser and then figure out the process that is related to the specific tab that you want to debug and then attach to that process. So we are automating that using some bit of PowerShell scripting. And the big challenge is trying to find the right function to look into. So luckily, all the browsers, all the major browsers make their symbolic debugging information available. So that is valid for all the different IE versions and also for Chrome. Just a word of caution, if you're trying to do Chrome debugging, the debug symbols for Chrome for each version are like around 1.2 gigabytes. So WinDebug has the nasty tendency to actually load all those debug information into memory. So if you're running this from a virtual machine, you better allocate a lot of memory for the VM, otherwise it's going to crash the VM. Well, not the VM, but basically crash the debug session. So the point is to try to find the right function, and we're typically looking at evaluations. So evaluations will be resolved by looking at the symbolic expressions, the symbolic function names. And I'm not going to go all the way through how it works because we're releasing the tutorial, as I said. But the point is that once you figure out which function implements the evaluation, you will quickly find that the most logical one doesn't really receive immediately the string argument for an eval as an argument. So you have to dig in typically deeper because most engines, practically all of the engines I've seen, actually do a pre-compilation of the eval statement. So if they have to run it again and again, they don't need to reparse it. So typically there will be some sort of a cache, and those cache functions will play a key role in getting your task done. So that those key functions will receive the argument that you're after. Now, after you found the function entry point and you set up the breakpoint, you have to understand how the arguments are being passed to it. And unfortunately, for Internet Explorer, although you have the debug symbols, you don't have the private symbols, only the public symbols. So the function arguments are not so simple to figure out. So while Mona does a fantastic job, and I can only applaud the creator for making Mona and releasing it, I, for the life of me, couldn't figure out how to figure out a way for a memory address that I was able to find to get a complete chain starting from either register that I have or an element on the stack to put together a chain of pointers. So for that, I'm releasing a tool called chain.py that works exactly that task, starting from either a register, like ESP there, but it could be the ECX register. Typically, it's either one of those. So either you're starting from the stack or starting from the this pointer that the ECX is typically pointing to, and you specify the number of D words you want to scan, the range of D words, and the -L is the reference count, so how deep you want to check for a pointer that is actually pointing to the target address specified in the -A argument. Now, once you figure that out, you may find multiple addresses just coincidentally point to the same point, so it will take a bit of trial and error to figure out definitely the one. And for this reason, we're going to do a bit of stress testing to figure out that if we found the proper chain of pointers. Okay, so once we've figured that out, we need to automate things. So we come up with a WinDebug script file. The WinDebug script is going to help us deal with a lot of manuality that would otherwise be needed. So set up a unique log file. Would be nice to have each session logged to a separate file, right? There might be a lot of exceptions that occur naturally within the application, and you don't want to break on those. So you might want to ignore certain exceptions while catch other ones. And I have to be honest, this is where WinDebug is showing its worst in terms of user friendliness. So trying to put out the for each is something taking me literally hours. Now, I'm going to try to do a demo here. Hopefully it will work. Okay, so let's see, how can I zoom the text? So it is as simple as this. You open a log file, you make sure that you don't catch all those unneeded exceptions. You want to make sure that whenever, and ultimately your goal is to catch exploits, so when the browser is actually crashing. You want to make sure that when the application is crashing, you close the log file, you set up a breakpoint, and you start a thing. So starting with the most simple example would be this. You only have a simple eval. Now, the reason why I'm using string concatenation there is you don't want to confuse the source code with the argument. So hunting for the egg, like my egg equal 1, will not be part of the source code. So the next case is a bit more demanding one. It's just going to do a bit of a iteration with a bit of complexity and do 100 evals. And ultimately, we're going to get as far as try to stress test it with the ultimate eval bomb. So this is a recursive evaluation, which will end up crashing the browser. Typically, depending on the browser implementation, sometimes it just ends up in a Stack Overflow. And to come to the point of this whole exercise is we're trying to look at how the actual deobfuscation is happening. So that said, let's see how we can try to use this. So it's as simple as starting up the browser, opening up a tab, and then opening up the logging PowerShell thing, which starts NTSD. So this is something I didn't mention. WinDebug has a GUI. NTSD is the command line counterpart of it. The very same thing as just command line. So for those of you out there who are wondering whether you can do nasty things with the debuggers as attackers, yes, you can. You might want to watch out for NTSD executables lurking in your environment because they can be mean as well. So once it's set up, you just try to navigate, and the logging is already starting to happening in the other. So here you're seeing the little simple evaluations. Now we're going for the longer evaluation with 100 iterations. Or we're going to do the obfuscated thing. So it's already logging the deobfuscated string at the bottom of the screen. I'm going to show you later on how you can read it easier. And finally, I'm going to show you the eval bomb. Yeah, I put it in the background while it was running. So, literally thousands and thousands of it happening. So once we look at the logs that are produced for each of them, we'll see something like this. So here are all those things that happened during the evaluations. If we go down a bit, probably should have done such a long cycle. Here you will see the simple deobfuscation that has happened. So this is already the deobfuscated string. And OK, so let's move on to a real thing. So I'm going to look at an actual exploit. So this is using an exploit on a use after free, putting together a ROP chain and doing a DAP evasion. And this is the actual source code for it. Now, I spent quite a bit of time to try to obfuscate it very heavily. So I ended up with something like this. This is a multi-stage obfuscation using a different number of techniques. So this is completely unreadable for the human eye, obviously. So let's see what happens if we try to do this. Again, I'm going to start the browser, start ilog. And let's see what happens. OK, so two things you should notice. Let's just open up the log in a more readable format. I can even turn on the highlighting. So this is already back to the deobfuscated string, although it's not pretty printed, but I will leave this up to you to do the pretty printing. And the more interesting thing is that we are actually getting a crash here, which is being caught. So right now we are in the debugger, in a live session, where as you're trying to move through, you can see that you are right before the exploit happening, and in a few moments, we're going to do the virtual protect, push ESP, and this is when it's jumping to the heap already. And probably you can recognize this already. This FL DPI wait FSTF, this is already part of the Metasploit code. So you got a deobfuscated code, and you've been offered the malware on a tray because it stops right before executing, and actually you can directly look at the source code, so you don't even have to replay the whole thing because you have the open debug session at your fingertips. Okay, so for future plans, we want to add a bit more documentation to the different browsers. So as I said, this has to be maintained for very different browsers because the code base is very different, the function names are different for obvious reasons, and even the module names are different. So in i8, the JavaScript is hosted in a JScript.dll. On the i9 Plus, it's called JScript 9. As from Edge, it's called Chakra. Obviously, you all know that in Chrome it's called V8, the engine. It's actually in a process called, in a DLL called Chrome Child. So I'm providing all these debug symbols for you to later reference to figure out the further details for your own needs. Now, for catching Metasploit shellcode, this is something that we wanted to try to see if we can catch them very easily. The most predominant cases that we see in Metasploit code are not so much the shellcodes as much as the Shikataganai encoder. So that's probably the most successful one, evading most AV engines. This might be an explanation for that. So Shikataganai has a very strong signature. So once you set up a breakpoint for the virtual locks and the virtual protect calls, then you can actually sniff at the pointers to the memory page. Now, the one last thing with the setting up calls for virtual protect and virtual alloc is something that I need to mention. It has to be done very carefully because the browsers naturally do some allocations for obvious reasons. So I'm also giving out some instructions on how to filter out the legitimate calls versus the non-legitimate ones. It's not really rocket science. So that being said, the source codes are available at those GitHub sites, and here's the contacts for both Csaba and myself. So with that, I guess we're opening up for questions. Yes. If any. All right, so then thank you very much for your patience and attention. Knowing that it's Saturday afternoon, it's a welcome thing. Thank you.
Thank you.